This video is going to get you started with Teamwork 7.2, although what we're going to look at here is finding an expression for the power absorbed in the resistor. It says using S-domain analysis. There's multiple types of S-domain analysis that we can use. We can do write time domain equations and do the Laplace transform of the time domain equations, and that's what we'll look at in this video. Or we can create an S-domain circuit where we model the initial conditions in the inductor. So one thing I want to make sure of here is that we understand power in the time domain versus power in the frequency domain. So that's why we're going to look at it here. And then I want you to complete Teamwork 7.2 where you're analyzing the other different methods. This is a simple circuit. We could solve it in time domain, and we want to make sure we can solve it all our different methods in frequency domain so that we become experts at our theory and our problem-solving process. So when we get to more difficult circuits, it just really becomes our circuit analysis techniques and our algebra. All right, so what are we trying to find? We're trying to find the power in the resistor. So that power in the resistor, if we can find the voltage, it is time domain. So if we can find the voltage in time domain, we can square that and divide that by 2 ohms, and then we'll get that power. What we need in order to do this problem is we need to know our initial conditions. Since we have at t less than 0 just 9 amps, at t just greater than 0 we have 9 plus 25 amps, 34. So that's when we're switching this current on. So let's take a look here. We can just write now our nodal equation. So our nodal equation to solve for this voltage, we can just use our V over R, which that's our V over 2 ohms, plus the current through the inductor, that's our 1 over L, and we integrate from 0 to t, really should be 0 minus, of the voltage, and we have to add back in that initial current. And what we have driving then at that point at t greater than 0 is 34, and we're going to write that 34 as 34 u of t. So our V over R, since R is 2, that's our 0.5 times our time domain voltage. This is still time domain equations. Our 1 over L, that's 0.1 henries, so 1 over 0.1 is 10, and we're integrating again this voltage. What we want to solve for is the voltage, so we're leaving that as V, but now when we're adding in this initial condition, we're writing that 9 amps as 9 u of t. Again, that's key. We've pointed it out a few times. It's not just 9. That would our Laplace transform of just 9 would be an impulse function. It's 9 u of t, so the Laplace transform of that is 9 over s. The Laplace transform of our integration is the frequency domain voltage divided by s, and now we're multiplying that by 10, and this is just 0.5 times our frequency domain voltage, and 34 u of t gives us 34 divided by s. So that's our inverse Laplace transform of this time domain equation. Very powerful technique that we can use here because we know the Laplace transform of the integral and the derivative. In this case, it's the integral we're using. So then once we have our voltage equation here, now we have to use our algebra. We want to isolate our voltage. We want to make sure we maintain that our variable is S, our frequency, and then we can go through our steps to isolate our voltage and get our voltage equation of S in a form that we can do our inverse Laplace transform. So you can pause the video, make sure you can go through these steps, but once we have it in this form we can use our Laplace transform table, and this is just an e to the negative 20t u of t times the 50. So that's our voltage. It's microvolts because well, I guess this was amps. I thought it was microamps. So if we'll ignore, we're going to assume here that we were using microamps. That's why I have, if we were using microamps there, we just have to insert the micro back in. So that if that was microamps, then we get microvolts. And our power then, we just need to square that and divide it by 2. If it was microamps, we'd end up with, when we square it, 10 to the negative 6 squared is 10 to the negative 12. And our e to the negative 20t becomes e to the negative 40t, and we would end up with 1.25 times negative 40t nanowatts. And again, you can pause the video, make sure you correct the fact that this solution here was assuming we had microamps for a current source. we've solved the problem. We made sure that we did not solve for power we're not solving for average power, we're solving for time domain power, so we have to convert back to time domain. We solved this by just writing an equation, our nodal equation in time domain and taking the Laplace transform of that nodal equation. If we also wanted to find the current through the inductor at this point, well, then we could use our IL is equal to the integral of VL dt plus our IL of 0 minus. And again, we're going to make sure when we do that, when we add that plus IL of 0 minus, we have the U of t there. So our Laplace transform of that equation, our frequency domain current, we have 1 over SL, our integral is dividing by S, and then we're adding back in that IL, that initial condition becomes IL over S. So then we can go through that and we can solve for IL, substituting in for VL what we solved for on the last page. It's the same V, and we can solve for our current, and we can end up with our our frequency domain version of that current, and then that's going to transform our IL of t then is equal to our we'd have to do our partial fraction expansion. It's going to be an A over S plus B over S plus 20 plus our 9 over S. And we can find our A by substituting in a 0. We take this, we cross that out, substitute in 0. We're just looking at this portion here, right? So that we substitute that, that's going to be 50 divided by 2, that's going to be 25. And our B, we're going to then cross out this, and we're going to plug in negative 20. And so that's going to be our 50 over 2, and that's also going to give us, I think, a 25 there. Yeah, but so actually that's going to give us what, a negative 25, because we're plugging in a negative 20 here. So that gives us a negative 25, and finally our IL of t is going to be equal to our when we sum these up, the 25 plus the 9, that's 34 over S. So that just becomes our 34 U of t, minus our 25 e to the negative 20, yeah, the negative 20t U of t. And that we can go back and get, we can solve that in time domain, make sure that you can do that as well. This should get you started with teamwork. I think it would say 7.2. And then what 7.2 is going to ask you to do is, instead of using our initial, our time domain equations to model our initial conditions across this inductor, model it as a current source, and then model it as a voltage source. So we have 3 different ways we can solve this problem. Well, 4 if we include time domain. And then we have all our problem solving strategies down, and then it just becomes increasing our ability to solve longer problems with more difficult problems, and then when we're doing it in S domain, it becomes our algebra as a function of S. All right, good luck with Teamwork 7.2.